Welcome to this second lecture. We are still continuing the theme microwave radiation fundamentals. So, we have seen the inhomogeneous Helmholtz equation in magnetic vector potential in the first class. Now, we will find a solution to that with a simplified case. First, we will consider a current distribution which is very fundamental, but which is very fictitious in nature, that is called Hertzian dipole or electric Hertzian dipole. It is an electric dipole. Also, this is called a current element. Interchangeably, there are many names to it. Now, this is actually a fictitious why? Because first let me draw the current element. As I have already shown that in Cartesian coordinates, the magnetic vector potential and the current density vector, they are collinear. So, it is easier to find out magnetic vector potential in Cartesian coordinate. So, I have drawn a Cartesian coordinate. Let us say that this is my z direction, this is my left handed system. Now, there let the current element is centered here. This is a very thin, its length is infinitesimal, it is a very thin current, but it is carrying a current I. So, this is generally always written as IdL, that means I is the length and dl. So, I is uniform throughout in magnitude and phase, but after reaching here there is no I, after reaching here there is no I. You know that this type of thing cannot exist in practice, that how I will put this current element, but we will see that to understand radiation this is a vital concept, because the radiation that takes place from this type of current element, that is present in all types of antenna radiations, and also will be actually breaking a distributed radiator, because all radiators are distributed, antennas are distributed structures, and they can be broken into these current elements. So, that is why this is fundamental. So, we consider that this I is a time varying current of frequency omega, etc., and let us say that we are observing it at a point, field point R. So, that means in generally field points are always specified in terms of the spherical coordinates r, theta, phi. So, at a point P we are interested to know what is the electric field, what is the magnetic field at that point. So, I again remind you that this is the direction of the radial vector at point P, the direction of the a theta vector will be like this, and a phi vector is orthogonal outside this plane is this. Okay. So, let us consider this radiation. So, a short thin filament of current located at the origin, oriented along the z axis. So, now we can say what will be then current density, that will be Jz into Az is and we have found that this value is ideal Az. Now, so this source distribution, if we you see this source distribution is definitely spherically symmetric, because the source does not have any theta or phi variation. In all theta and phi it will be looking same, definitely it has some r variation. So, we can say and we have already found that the source that again let us look that the current density vector is z directed. So, we can say that A also will be z directed, magnetic vector potential A, that will be also. So, I can say that magnetic vector potential will be Az, and from the symmetry I can say that Az will be a function of r, and Az is not a function of theta or phi, because the source is spherically symmetric. Once this is there, I can write. So, what will be my equation? That Laplacian equation del square Az plus k naught Az is equal to minus mu naught Jz. I will have to solve this equation. So, I can immediately write the del square equation in the spherical coordinate. So, I will write 1 by r square del r square del Az del r plus k naught square Az. Here you know that solution of any inhomogeneous differential equation, first we solve the homogeneous equation. This is an homogeneous differential equation that gives us the general solution, and then we add to that the particular solution. So, that we will do by that time putting the source value, that means the Jj value. So, first we will doing the homogeneous part of the solution. This you know from your knowledge of differential equation solution. Now, the solution, as you know that in second order differential equation we first find the solution. So, solution will be obviously have. So, Az is a function of r. Let us put that the function is, that functional dependency is 1 by r, and psi is a constant. So, if we do that, then we can find what is, instead of del z I can write dAz, because it is only a function of r. So, dz dr will be, this is simple mathematics, you will be able to do on your own. Similarly, you can find what is r square dAz dr, that will be r d phi dr minus phi, then del r square dS, that will, after some substitution I am not doing, it is simple you do, because it is a only one variable dependence. So, we can say that this 1 by r square del r square del S del r, that will be 1 by r del square phi, sorry, it is d square phi dr square. So, this we have got one part. Now, let us put it. So, we can say that 1 by r d2 phi dr2 plus or we can write it as d2 phi dr2 plus k naught square phi is equal to 0. So, this is a simple scalar second order equation. So, differential equation. So, all of us from our college days knows this solution. This is simple harmonic motion solution. So, what will be the solution? We know that phi will be equal to C1 e to the power minus j k naught r plus C2 e to the power plus j k naught r. Both these solutions are possible, that is why we are writing it as superposition of them. C1 and C2 are unknown, that is value to be determined. This is mathematics, but physics says that out of these one solution is not acceptable. Why? Because it is a radiation taking place. So, radiation means transport of energy. So, at a infinite distance from the source, the value of the field should go to 0. So, out of this actually what is, if I choose phi is equal to C2 e to the power plus j k naught r. You know this is an wave which is coming inside, and if I put r is infinity, then this value becomes infinite. So, that radiation condition says that this is not possible. This wave, any wave coming here at infinite, it should have high infinite value. So, this is not possible. So, this solution is not possible. So, acceptable solution is okay. Now, let us, this was a phasor solution. So, if we now write the time variation, then it will be C1 e to the power minus j k naught r plus j omega t. And already if you recall that when we define the wave number k1, that time we have said k naught is equal to omega into square root of mu naught mu epsilon a for free space. So, that is actually c is the speed of light in free space. So, in that terms we can write that phi r t, that will be C1 e to the power j omega t minus r by c. So, this is definitely an equation of a wave which is travelling outward and reaching the point P in my drawing, that the observation point P at a delay, time delay of r by c. So, this phi, which is called retarded potential, because due to this delay the potential is getting retarded in time. So, this is a wave solution, and here still we have to find the value of C1, that we will do. So, again if we suppress the time variation, we comes back. So, what is our AZ? We have assumed the solution as AZ is equal to phi by r. So, now we will have to write that AZ will be C1 e to the power minus j omega r by c by r, or in our previous nomenclature, that means in terms of k minus j k naught r by r. Here you will see that In time domain generally we all bring this k naught as omega by c, but in antenna parlance we will see that this wave number domain has some advantages. That is why we prefer, when we are in phasor domain we are considering the radiation things, we do it, but if we come to time domain generally we bring back through this relation omega. Okay. So, this is the solution, A z is this, C 1 is yet to be found out. So, that means this is the solution for the homogeneous part or the general solution of the differential equation. Now, we will have to solve the inhomogeneous part to evaluate this C 1. Okay. So, what we have done, from the current element we found out that okay, this is the direction of the current. So, accordingly we found that vector potential also will be z directed. We assume that vector potential is some constant by r. By that we found that okay, it is satisfying the wave equation. So, we have found the solutions. Out of two solutions, one we have physical consideration, radiation condition, from that we have discarded. We have kept the valid solution and we have found the general solution. Now, we will have to put the value of C 1 from the inhomogeneous part, and that will be our thing. So, next we are finding the inhomogeneous solution part. So, what is the equation? Write the inhomogeneous equation. This was our inhomogeneous equation. Now, what we do, you see what was our solution, A z was, here is a problem that if we want to determine what is the value of A z at r is equal to 0, it is a division by 0 case, because phi is a non-zero and fine, psi function is non-zero and r is 0. So, this happens in all the electric fields, magnetic fields, you have seen these, that at r is equal to 0 we cannot define it, but the source or the actual we call it singularity that is present there, the strength of the source, that will miss out if we do not consider the r 0 point. So, what is the way out? We look at a very small volume around the source. We are not exactly r, but we know that very near to r, if we can enclose the source, we will get its radiation effects, that means the effect of the source. So, that is why we actually, to find the source strength, we do this, that we integrate the both sides of this scalar equation, scalar Helmholtz equation, over a small spherical volume of radius r. So, that means if we have this current element source, this is our source IDL, over this we put a spherical volume of radius r naught, we find out this and then we force that r naught to go to 0. So, that will be the effect of this source. So, this is the idea. So, we know we can use divergence theorem, and what is del square A z? Del square A z is nothing but this is the Laplacian. So, that is A z is a scalar. So, gradient of that, divergence of that. So, now using divergence theorem, can I write this? Del square A z dV is equal to del dot del A z dV, and that now if I apply divergence theorem, that will be a surface, closed surface del Az dot ds. Now, what is the ds vector? In spherical coordinate, we know the ds vector is ar r naught square sin theta d phi. So, putting this in the scalar Helmholtz equation, which we are doing. So, in scalar Helmholtz equation, while integrating, we actually our actual equation will be, this is a volume integration del square is a dV plus k naught square dV is equal to minus volume integration mu naught Jz dV. This is the integration of inhomogeneous Helmholtz equation. Now, there we have already simplified these, del square Az dV will be actually a surface integration. So, I can write that. Now, let us look this term Az dV. Az dV. Az I know. What is it? C1 e to the power minus j k naught r by r square sin theta d theta d phi dr. This is our dV in spherical coordinate, r square sin theta d theta d phi dr. So, this term you see that this is proportional to r. So, finally, when I will put that limit r naught tends to 0. So, this is proportional to r. So, this will become 0. So, this term I can forget. Also, previous page. So, this term I have put that this is 0. I am left with this term. Let us see this term. This term is we have seen that this term is nothing but, because I have only a current element IDL. So, volume wise if I integrate, I will get IDL, and so this term already I got. So, this term also I have solved. Now, this term, let me further manipulate this term. What will be this term if you see? What is actually del Az dot AR? Others will be coming later. So, this means what? This is nothing but del Az del R, and I know the value of Az, C1 e to the power minus j k naught R by R. So, if I do this, I will get minus 1 plus j k naught R C1 e to the power minus j k naught R by R square. You will see this, that if I do this, it will be this. So, everything now is ready. I am now putting it limit R 0 tends to 0 . Already this is a surface integral. So, I will have to, so, this is minus 1 plus j k naught r naught C1 e to the power minus j k naught r naught sin theta d theta d phi is equal to minus mu naught I dl. Now, these are all constant things. So, sin theta d theta d phi, and I will have to put these value things. So, phi will be 0 to pi, this will be 0 to 2 pi. So, this one then will become minus 1 plus j k naught r naught C1 e to the power minus j k naught r naught, and due to integration there will be 1 2 pi and 0 to pi sin theta d theta is another 2. So, 4 pi into this. Now, if I put this, and this is equal to minus mu naught I dl, but here is a limit, everything r naught goes to 0. So, if this goes to 0, this term cancels. So, this term goes to 0 with the thing. So, I get the final thing minus 4 pi C1, this term also 1 is equal to minus mu naught I dl. So, this helps me to find the value of C1 is nothing but mu naught I dl by 4 pi. So, we can now find that actual solution is Az is what? Az is equal to mu naught I dl by 4 pi e to the power minus j k naught r by r. So, you see this C1 actually represents the source strength, ideal is the strength of the source, these are the constants etc. So, Az is this. So, we can say that finally, we found the A vector for the current element, that is mu naught by 4 pi I dl e to the power minus j k naught r by r Az. So, solving the Helmholtz equation, inhomogeneous Helmholtz equation, we could obtain the magnetic vector potential. So, this is a remarkable achievement that we can find this. So, now I can say that if I have a current, the current element was y directed, then this edge, instead of A z, that time it will be A y, and this will be A y directed. If I have a current element in x direction, then there will be A x, that will be there, that directed. So, we can get now this. From here it is very simple to find out the first, the defining equation was H. So, what is H? H is 1 by mu naught del cross A. So, if we do that, we know A. So, if we do this, we will be able to find H, and we know what is E. E is, if we put this solution into the Maxwell's equation, you get minus j omega A plus del cross A by j omega mu epsilon. So, I know A. So, E can be obtained, or you can this first find out H, then put the H into Maxwell's equation, you can do, or directly from here also you can find out. So, this is the whole journey that we can solve for the all radiation, but we have not evaluated this. So, we will have to evaluate that, and we will have to express it in terms of field coordinates. So, field coordinates are generally spherical. So, that we generally express in spherical coordinates, and we will convert that, we will find the fields, and will by that we can analyze the structures. So, we have done an useful thing. In the next class, we will see what is the importance of this derivation. Coming through this potential route, we have seen we can simplify, because knowing the current given source current's direction, we can easily find the vector potential, magnetic vector potential, and from magnetic vector potential easily we can find the magnetic field and electric field that is radiated by the antenna at the points. Okay. So, some more steps are there to actual writing the expressions of this, that we will take in the next class.